All right, now let's get in there and mess around with equilibrium. Kind of mess with the whole system. So how do we do that? So there is a principle, Le Chatelier's principle. Don't get me started on pronouncing that. I can't actually say it the proper way. Like I've tried, but it's better than saying Le Chatelier. So Le Chatelier. I know it's mangled. Anyhow, he says that if a system at equilibrium is disturbed by a change in the temperature, the pressure, or the concentration of one of the components, the system is going to shift its equilibrium position so as to counteract the effect of the disturbance. All right, so remember, an equilibrium position is just a set of equilibrium concentration values that equals KEQ for your system. So it will adjust. This is weird. It's almost like they're thinking. You can go in and like mess with something, and it's going to reestablish equilibrium. All right, it'll be in a new equilibrium position, but it's kind of cool. So let me give you the old fish tank example. It works. It's something big you can wrap your head around as to what's going on. So let's say we have like a big aquarium, and we got this permeable barrier separating these two sides. So maybe like some kind of thick cloth, something that the water can flow through, just not gush through. All right. So it can make its way through here. And I know when it's just sitting there on the table, it's at equilibrium. I know there's water flowing through this way and that way, and there's doing it at equal rates, right? That's what equilibrium is, equal rates. How do I know that? Well, if it was flowing more to the right than it was to the left, then there would be more water on this side than there is on this side, right? Like that would, if it was just pushing more this way, it'd be like the osmotic pressure thing I was telling you about earlier. Anyhow, back to this. I want to mess with this. I want to disturb my system. So I'm going to take a bunch of water and I'm going to dump it into the left side of this tank. All right, that's going to be the disturbance. All right. It's been disturbed. How does the system react to this disturbance now? Well, now, do you think it's flowing evenly across this barrier anymore? Definitely not. There's more water flowing this way than this way. So more water's going to the right than there is going to the left, at least for now. And because there's more water going right than left, that means that this side's going to drop, this side's going to go up, and boom, eventually they'll reestablish equilibrium. All right, so now it's hit its new equilibrium position. All right, so how is this like a chemical system? All right, if I have this system, going back to my generic A, B, C, D thing going on here, if I add A, right, so I'm going to go into my system, it's already in equilibrium, and I'm going to mess with it. I'm going to add a bunch of A to the beaker, right? That's going to react with some of the B that's already in there, so that concentration is going to drop. But these are going to go up, all right? It's going to do this in such a way that it still equals KEQ, all right? So if I add A, this drops, these both go up. So what we say there is we had a shift to the right, all right? Because all of a sudden both of these have gone up compared to our previous position. Same thing if I add B. If I added B, all right, B is going to add or react with A. So A is going to drop, and then C and D are going to go up in such a way that this all equals KEQ. So that's another shift to the right. If I added C, right, if I increase the amount of C in my system, all of a sudden that's going to drop. These are going to go up. So now that's a shift to the left, right, because the A and B concentrations both go up in this new position. Right, add D. So anytime I add something, it always shifts the position to the other side. So the equilibrium position always shifts away from the side you're adding to. So what are you adding? A, B, C, or D? So if I'm adding something on this side, it's going to shift equilibrium to this side. If I add something on this side, it shifts the position towards this side. So it always goes away from the side you're adding to. What about taking stuff out? Let's go back to the fish tank example here. If I just take a big old bucket, and scoop out a bunch of water from this side, obviously this is going to start pouring back in here. It's going to kind of fill it up. The chemical system, equilibrium system, is going to react in a similar kind of way. If I take out C or D, or C and D, this system is going to try to replace that. It's going to try to increase those concentrations to make this KEQ value equal what it should equal. All right, so it's going to disturb it until it like reestablishes those concentrations that will equal the KEQ value for this particular system at this temperature. So, very cool. So in a nutshell, all right, I have some alliterative fun here. Equilibrium shifts away from the side you add to towards the side you take from. All right. The other thing, our fish tank, like the KEQ, right? Again, just visually, you're looking at it like, oh, equilibriums would have equal amounts. No, no, no. Remember, we can have really product favored or really reactant favored systems where, one side is millions of times greater than the other side. So again, don't let the fish tank totally fool you there. But this part, definitely take that with you. Away, add, towards, take. We also mentioned temperature and pressure, so let's go into those. So I just talked about concentration. Let's get into the temperature and pressure stuff. Let's go pressure first. So how does pressure affect equilibrium? Let's get that in there. All right, so here's my equilibrium system. Imagine I have this balloony guy here, and this balloony guy here, and they're inside this giant piston. And this piston starts crushing down on it. So I'm going to increase the pressure on my system. Who do you think feels it first? This one, all right, the big one. All right, how does it relieve that stress? It pushes over to the small side. So in an equilibrium system, how can you tell which side of the equation is bigger? We look at moles of gas. Right, you look at the moles of gas. Whichever side of your equation has more moles of gas, right, that's the big side. And when you increase pressure on that system, it's going to force it over to the small side. That's how it adjusts for that pressure. Right? So if you have more reactant gas molecules and you increase the pressure, it's going to shift the equilibrium to the right. Right? That's what we just saw on that previous slide. If I had more product gas molecules and I increased pressure, that would shift it to the left. If you decrease the pressure, it does the opposite. Right? If I take the pressure away, then it's going to want to go shift to the side that takes up the most amount of space. So let's look at this thing really quick. All right, CO plus 3H2, CH4, H2O. If I increase pressure on this system, which way is it going to shift, left or right? All right, let's look at moles of gas. 1 plus 3, there's 4 moles of gas here, there's 2 moles here. This is the big side. All right, so if I increase pressure on this system, it's going to force me over here. So it definitely push me to the right. All right, let's talk about temperature, the temperature stress. All right, temperature, heat. Right? Heat's produced or absorbed. Right? How do you know if a reaction absorbs or releases heat? It's the sign of delta H. So you look at the delta H. Right? Negative delta H means it's exothermic. That means it produces heat. If the delta H is positive, that means heat goes into your system. So we can put heat into the equation just like it was a reactant or a product. And then we go back to this. Add, away, towards, take. All right, it's going to shift away from the side you add to towards the side you take from. So if I have an exothermic in the forward direction, so exothermic in the forward direction system, and I heat the whole thing up, it's going to push it back towards the reactants. It's going to push it to the left, right? Because heat's over here, it's on the product side. If I have heat on the reactant side and I heat that up, that's going to push me over towards this side. All right, we'll deal with this one in either over Zoom or in person or something. All right, but this is kind of a cool system where you can see which way the equilibrium is shifting based on the color. So let's wrap this thing up. So far, rating KEQ. So it's products over reactants, coefficients become exponents, solids and liquids do not go in. I'm going to say it again. Products over reactants, coefficients become exponents, solids and liquids do not go in. If you know how to write KEQ, that's good, because there's lots of different types of KEQ, and we're going to go over those in the the end of this chapter and into the next chapter. You're going to see some more KEQs, different flavors of KEQ is what I like to call them. All right, and so when you're predicting equilibrium changes, just remember equilibrium shifts away from the side you add to, shifts towards the side you take from, and high pressure favors the side that has the smallest volume. So look at moles of gas to figure out which side is bigger. All right, that's that for the second section here. I will catch you in section 3. See ya.